Get started.
A very good afternoon to all. Honorable and a man of high integrity, our CEO Sri Pradeep Verma sir, Honorable the Registrar SBU, Professor Dr. VK Singh sir, respected Dr. Tarkes, Scientific Assistant Kit Germany, respected Dean Engineering and Applied Science Professor Shridhar B. Dandin sir, esteemed Sanjeev Bajaj sir, respected Manish sir, distinguished participants, all those who have joined from all over India, learned faculty members, students, and other technical and non-technical staff. A very good afternoon to everyone. It is a great honor and pleasure for me to welcome you all in today's technical session on modeling of thermal boundary condition in finite element simulation for precision glass molding. My name is Manish Agrawal, and it is my privilege and pleasure on behalf of Department of Mechanical Engineering to welcome you here today. Sarala Birla University is committed to actively raising the quality of life for every student. We want all, regardless of race, creed, or circumstances, to achieve their full potential. Our task is to make possible, our mission is to provide practical step-by-step learning. Your active participation is important throughout this session, and right now I have everyone on mute to avoid background noises that may distract you from listening to the webinar. Throughout the presentation, Professor Rajeev Ranjan sir will be managing the chat functionality, and you can enter your question and comments in the question box throughout the presentation. And if you miss anything, don't worry, we will be sending you the on demand recording when it is available. The esteemed speaker of today's webinar, Dr. Tarkes, Scientific Assistant in Kin, Germany. He is currently a postdoctorate employee at Institute of Engineering Mechanics, Karlsruhe Institute of Technology. This university is located in southern part of Germany in city named Karlsruhe. He is currently working on micromechanics homogenization problem and simulation residual stress in composite material. Earlier to this, he was postdoctoral fellow in Technonian Israel Institute of Technology for a year. In 2016, he completed his doctorate from IIT Madras, Masters in Material Science and Engineering from NIT Tirchi, and BTech in Mechanical Engineering from Biju Patnaik University of Technology, Odisha. If you look at his career, his journey has been from very local Indian university to one of the leading international university. During this journey, there are 8 international journal articles and few more underway to publish, few book chapters and several national and international conferences. He has always been a motivational for all his friends and colleagues. I welcome you from the bottom of my heart and thank you very much for bringing out time for the session in your busy schedule, Tarkes sir. Sir, I most humbly request you to start this session and enlighten us with your precious words and expertise. Thank you so much, sir. Please, Tarkes sir.
So, thank you, Manish, for this kind introduction. It was um, quite kindful of you. Before I start my presentation at the outset, first I would like to thank the CEO of Sarala Birla University, Mr. Pradeep Verma, and the Registrar Professor Dr. VK Singh, and Dean Professor Shridhar Dandin, and Professor Sanjeev Bajaj. So for giving me an opportunity, and it is quite nice and good that such webinar series and initiatives are being taken by Sarala Birla University for the student and as well as the engineering community in such crisis times. So on this note, we would just now get started with the topic of the on today's topic. So so today I'll be going to present on modeling of thermal boundary conditions in simulation of precision glass molding. So in this work, so this work was basically done at Indian Institute of Technology, Madras, when I was a doctoral student there. And there was a Indo-European simuglass project based on which all these works were carried out. and we had collaboration with Indian Institute of Technology Delhi and with Fraunhofer IPT Aachen, which is again in Germany, and CGCRI Kolkata. Now, if you look at on the slide over here, so if you look at on the slide over here, so you can see that there is a glass preform placed between the molds, and you can see that there is a virtual pressing or molding operation being done, and then at the end you have the fabricated lens. So so when I say lens, you have to understand that the surface finish of the lens has to be very high, because because this is being used for optical applications, and it has to be as precise as possible. And if you look at the molds here, these have got a mirror surface finish molds, and fabricating such molds is quite very expensive, and it's making some trial and error experiments is not feasible or acceptable in experimental conditions. So that is where the finite element simulation plays a major role in optimizing the process and minimizing the residual stress, or for the design of the lens. So all the way it helps. With this objective and with this motivation, first I would like to give a short outline what I would be presenting today. So initially I would be talking about the precision glass molding process and the machine. I will be showing out how the process is being happened. So this will help you in understanding throughout the presentation what is being done. And I would discuss then challenges in the simulation of precision glass molding. It's related to its material model of the glass and the boundary conditions. And then I would talk about digital photoelasticity of glass. And then I would discuss on modeling, how to model the heat transfer during the cooling stage of the precision glass molding process. I would be discussing some results related to this. And then what is the new findings with respect to simulating a sample plano-convex lens. And finally, I would be concluding and would be discussing about the current trends in glass processing technology and related to Industrial 4.0 and digital twin. Now, a special message for the bachelor students: they may not understand every aspect of the presentation. It's totally fine, because with the current set of knowledge you have, you may not understand everything. But what you should look at it is, you have to derive what kind of academic problems you could bring out of it, and then for your future career and future goals, what direction you want to go, you could decide. I mean, you could make a mind map out of this. So especially in the current trends in the glass processing technology and the digital twin, you would get a complete mind map of this, how the whole engineering community works on fabricating a particular product. Now with this, let's look into what's happening with the precision glass molding process. So here initially we place a glass gob between two molds. We have the upper mold and lower mold, and it is placed in a nitrogen environment. And in this environment, we switch on the heaters, and then we heat the whole assembly, and it's being heated to slightly above the glass transition temperature of the ceramic glass material. And then we press against these molds. We keep it for some time at this hot temperature, so that there is a uniform temperature distribution. And then after, you cool the glass and the whole assembly by slow cooling, and then subsequently by fast cooling. And then at the end, you would have the lens. And if you take a closer look onto the surface of the lens and the surface of the molds, you would see something as like this. So if you look at carefully onto the profile of the lens, which is in blue color, and the profile of the mold, which is in grayish color, so there is a very small deviation, which is about 9 micrometer. So on an engineering sense, one would say, oh, 9 micrometer is totally fine. I mean, it's acceptable, but it is actually not for the case of lens applications, because it has to be precise, because we have to keep it in mind that it is being used for an optical application, maybe for a microscope, or maybe for a CD players where you have a micro lenses there. So it has to be, the surface profile has to be as accurate as possible, very less than 1 micrometer. So this deviation would induce several defects in the lenses, and hence these products cannot be used for the desired application. So hence this necessary care has to be taken while fabricating the lens. And after the lens has been fabricated, at the end there is a residual stresses which is logged in the glass material, and due to which you would see that there is a residual birefringence. This term could be quite new for you. It is nothing but it is the lag in the polarized light rays. The speed at there will be a, if you go and look into the basics of optics, so there would be a phase lag between the polarized light rays, and that is what is being indicated as residual birefringence. And this birefringence is induced due to the presence of residual stress in the glass material. So we are not directly quantifying the residual stress, but indirectly we are quantifying it in terms of an optical quantity. So in simple words, so it ranges from 0 to 277 nanometer, which is actually quite high for lens applications. It has, the values has to be maybe less than 10 nanometers or maybe 5 nanometers or close to zero. But if such values are existing like 277 or 300, it's totally not acceptable. This could induce a kind of chromatic aberration in lenses, whatever you study in the regular physics related to the lens. Now, if you look at the precision glass molding machine, so this is how the molding machine looks like. You have the nitrogen gas flow, which blows nitrogen gas into the machine, and then you have a cooling plate in between, and then you have the mold inserts. And here you see the two glass preforms are being placed on the molds, and you have the surface finish, mirror surface finish molds over here. And when you are doing the pressing operation, this whole assembly comes down, and then the chamber has been closed. But if you take a very closer look to the assembly of the nitrogen gas pipe and the cooling plate, on a there are very small outlets through which the nitrogen gas comes out. So if you take a look into the picture on the right hand side, so this is the nitrogen gas pipe which is sitting on the cooling plate, and if you take a zoomed view, you can see clearly the outlet through which the nitrogen gas comes out. And now if I show you the complete 2D sector, the three-dimensional sector view of the whole machine. So this is how it looks like. So you have a nitrogen gas pipe through which the nitrogen gas blows in, and there are some holes over here in the molds, and then through these molds, through these small holes, the nitrogen gas comes out, which is the inlets to the nitrogen gas flow. And the green color, what is shown over here, is the nitrogen gas flow domain. So if you look into the gray color and the brown color, these are solid material. So there's solid mechanics plays a role, and the green color domain is fluid. There is a gas flow, that is a fluid mechanics domain over there. So which has to be solved. And to the whole assembly is being covered by a quartz glass casing, so which covers the whole assembly over there. And the nitrogen gas flows happens within this chamber. Now, if you look into the figure over here on the right hand side, so you can clearly see the slots through which the nitrogen gas comes out. I'm showing a 2D sector. I'm showing at the angle of 22.5 degree over here. So there are 8 channels. So they are repeating it by rotationally in a rotational periodic manner. So I'm showing the 45 degree solid domain over here, and this is the section shown at 22.5 degree. So at 22.5 degree, you can see clearly the channels through which the gas comes out. And this is how the mechanism of the gas flow happens over here. So the gas comes in, and through these slots, gas flows out, and then it flows towards upward. And there is a outlet pipe through which the nitrogen gas comes out. So this is how the nitrogen gas flow mechanism happen, and this is how the whole process happens, and this is the machine details. And now with this note, we will try to look into what is the aspects or challenges with respect to the simulation of the process simulation of precision glass molding. Now, typically, if anyone has done a simple finite element simulation, one should, in a very simple terms, I'm trying to present over here. So for a simple finite element simulation, you need basically material model to capture the behavior, how the material behaves at high temperature or low temperatures. And then you need boundary conditions, and then you mechanical boundary conditions, and as well as thermal boundary conditions. And then the whole boundary problem, value problem is being defined, and then it is being solved numerically. So these are, I'm not discussing on the numerical part, but now let's look into the material model aspects. So how does the glass behaves when the whole pressing operation is being done? So at room temperature it is elastic, at high temperature it is going to become soften, something like viscoelastic. It has got a rate dependent behavior, and then again you are cooling it, and you are the material is transiting to elastic behavior. So the whole transition happens to elastic, viscoelastic, and back to elastic. So this whole transition has to be captured. So let's look into the material model in details. So here I'm showing you the constitutive relations for the for the glass material. So if one is aware of simple elastic relations, sigma is equal to E into epsilon. For a three-dimensional problem, you have all the tensorial quantities now. You have second order tensor and the fourth order tensor, stiffness tensor. So the strain tensor is going to be over here. These are the elastic strains, which is being stored in the energy when you compress the material. There is the energy stored in the springs. And you so in order to compute these elastic strains, you need to subtract the total strain with thermal strain and the viscous strain. And the viscous strain, I'm assuming that the fluidic behavior is following a Newtonian kind of a fluid, and you have a stress strain relation for it, a stress versus strain rate relation for it. So here I'm considering that the deviatoric part of the viscous strain tensor is participating in relaxation, or in other words, the flow behavior is happening there due to the deviatoric component. So that is why you have a dash over here, and then it is and this is the relation what we use. And once you substitute the sigma over here and do a little bit of readjustment, you can express it in terms of stress relaxation time. So I'm using here a generalized Maxwell model to capture the viscoelastic behavior, and tau alpha indicates the relaxation time of each Maxwell branch. So here I'm indicating the Maxwell branch with a scalar quantities G, because I'm trying to say that only the shear components are being participating in the relaxation behavior. Now this is what is happening at higher temperature. So the material is softened, so it behaves like viscoelastic. So this is what you can do. But as I mentioned, at room temperature, it behaves elastic. So that means the relaxation time you could think it's becoming very, very large, or the viscosity of the material is very, very high at room temperature, and then it is not able to relax anymore. So that is why the relaxation time is going to infinity, and it has to be taken as a function of temperature. And this relaxation time, if you are defining it as a function of temperature, you can take a shift function which which takes into account these temperature effects for making transiting the relaxation time for a finite value to a infinite value. So this is the constitutive model what we use. And if you look at the thermal strain specifically, there is a non-linear thermal expansion what is happening in the glass material. And this is being taken into account by using Tool, Narayan Swamy and Mohinian model. This is very classical model, which is widely available in the literature. And one can look into the details of it. I'm not going to explain the mathematical aspects of it. So these nonlinear effects are being taken into account by using this model. And here we evaluate a temperature called as fictive temperature. This is nothing. This quantity is not a kind of a physical quantity, but kind of a artificial quantity, which indicates a kind of a artificial temperature which is present in the glass. And if you are able to compute this artificial temperature quantity, you would be able to capture the nonlinear expansion behavior of the glass. And without getting into the mathematical details, I would like to explain you what is happening with the physically, what is actually happening there, the nonlinear expansion, where does it come from actually. So if you look at the graph of the specific volume versus temperature graph of a typical glass, the glass would show something like this. So at higher temperatures, very, very higher temperatures, it is going to behave like a liquid. At intermediate temperature range, it is going to behave like a soften, like a viscoelastic. At room temperature, it is completely a linear elastic. So the linear elastic, what happens when there is a temperature change happening at a particular material point? Whatever the discussion is being done, this is at a particular material point. So at this particular material point, what happens when the temperature, if let's say it suddenly cools from, let's say, 30 degrees centigrade to 20 degrees centigrade, it's a it is in the linear elastic domain. And at room temperatures, the vibrational change configuration, the vibrational change modes of the molecules of the glass material changes instantaneously, and this leads to instantaneous behavior or instantaneous thermal expansion of glass. Whereas at higher temperatures, the structural vibrational change is not of so important. Structural change mechanism comes into role. So when I say structural change, it means that the molecules of the glass, the bonds, they break and they reform again. So that happens process very instantaneously. When I'm let's say cooling at a very higher temperature, let's say maybe 1500 degrees centigrade to let's say 1400 degrees centigrade. When I'm cooling it in that range, so there is a structural change happening very instantaneously. So if I'm talking about, let's say, intermediate temperature range, temperature range. So let's say the glass material is existing at T0 at some intermediate temperature range, and I'm cooling it to, let's say, T1. And then when the cooling happens at T0, let's say the specific volume at time t equal to 0. So when I start the process, to at time, let's say t equal to infinity. So after, let's say 30 minutes or maybe 40 minutes, the property is going to remain same. It is not going to change. But if I, when I'm cooling it from T0 to T1, suddenly what would happen is the at that instant, the specific volume is going to remain a specific value. And after, if I allow, after, let's say if I'm checking the property after 30 minutes back again, it is going to change. It's not going to remain constant. So this is what is the causing the nonlinear effects, bringing the nonlinear thermal expansion effects. So this is how typically the property versus time graph would look like. So property at time infinity at T0, you have a constant value, but when suddenly I'm changing the temperature, there is a instantaneous response. And this instantaneous response is happening due to vibrational change, and the structural change where the bonds are breaking and reforming again, that causes the time dependent response, and due to which you would have a time dependent response here. And at infinity, you would see the property over here again. So that is what is shown over here. So in the intermediate temperature, you have vibrational change as well as structural change. The structural change happens due to time, is a time dependent process, and due to which you have the time dependent effects during the cooling process. And if you draw slopes of the glassy line and the equilibrium liquid, so the intersection of this point is called as the glass transition temperature, and it depends on the cooling rate. And the intersection of the line after some time, whatever time I take, and then if I draw a parallel a line slope parallel to this glassy line, the intersection is called as the fictive temperature. So this is a kind of a physical meaning attached to this fictive temperature, but it never exists in the glass. Actually, it's not measurable quantity. So, so this is how nonlinear effects is being taken into account by the tool known as Sami-Mohinyan model, and this is what is being done in mathematics. So this is what I have discussed now with respect to material model. Now let's look into the mechanical boundary conditions. So I'm not going to discuss how the experimentally the boundary conditions are being measured. So there is a, so as you have seen during the pressing operation, there is a glass mold contact boundary condition, and there is a force boundary condition acting on the molds where the pressing operation happens. The force boundary condition is a easily measurable quantity. There is a standard devices for it, and you can look into this reference for the details of the process. And for the glass mold contact boundary condition, there is a specific experimental setup which has got with, I mean, it is existing at Fraunhofer IPT. So this is quite a expensive experimental setup. So they have done the experiments to measure the friction between the glass and mold contact. So the mechanical boundary condition is nothing but the friction what happens at the glass mold interface. You can look into this paper particularly for details if you are interested to. I'm not going to present details of the experimental setup, so but you can look into through this reference. And this is what happens with the mechanical boundary condition. And if you look into the thermal boundary conditions now, there are two issues here. One is the glass nitrogen interaction, which could possibly happen, depends upon the product, what is the size of it. Let's say if the whole mold assembly is being closed, there is no glass nitrogen interaction. But if let's say the molds are open, there is a glass nitrogen interaction effects. So it depends, I mean, depends upon the situation. So, but this boundary condition has to be taken care. This is one aspect. And if you look into the literature, there has been several values being taken, the heat transfer coefficient values. These are like, I mean, they have assumed that the mode of heat transfer is natural convection or forced convection, and then based on that, they have taken several values. I'm not citing the main important, all the references here. You can look into the paper for all the details. And what we did actually is we simulated the nitrogen gas flow mechanism, nitrogen flow, to investigate what actually the mechanism is happening during the cooling stage. So if you look into this slide over here, as I have already explained the details of the nitrogen gas flow, how it happens here. So I'm showing only in this region over here, close to the region of molds. So there is a circular kind of glass disc placed in between the molds, and then for this kind of geometrical arrangement, the simulation has been done because it is quite simple and it is perfectly rotationally periodic, and all the analysis becomes quite simple to handle. So for a flow rate of 30 liters per minute, you can see that the nitrogen gas is exiting from here. It is striking to the quartz, this glass casing over here, and then nitrogen gas flow happens. The temperature of the molds and the glass are at 823 degrees centigrade, and you can see that there is no more kind of forced convection happening here, because the gas is at 20 degrees centigrade and the glass is at 823 degrees centigrade. If there would have been forced convection, you would have expected a blue kind of color over here in this region. I'm showing the contour plots for a temperature between 20 degrees centigrade to, let's say, something maybe 600 degrees centigrade. So here you can see that there is a gas conduction actually happening, and as you move slightly away from the this region, there is a gas flow happening. So there is a gas conduction happening till this region, and after that there is a gas flow, and then the hot gases are being excavated out. So this is what is the mechanism through which the heat transfer is taking place, and taking into account in the finite element simulation is quite challenging now, because we don't have any such kind of facilities in modeling the heat transfer. So in finite element simulation, so we can model is the heat, we can take a heat transfer coefficient value. So but we couldn't get any values for it because there is no forced convection happening. Now we did it for higher flow rates. We took for about just a minute. So we took we increased the flow rate for 50 liters per minute. So you can see that the nitrogen gas is trying to enter into this domain, but it is unable to. And at 80 liters per minute, still it tries, but there is no forced convection happening. There is always a gas conduction, and then there is a flow field. So this is how the cooling actually happens. So this was a contribution from my side into the literature of the precision glass molding process. And then there is second thermal boundary condition, which is the glass mold interaction. So during the pressing operation, there is a glass mold heat transfer happening, and also during the cooling stage. So due to which the glass is able to cool down. So in literature, again, there are several values being used, and there was hybrid kind of experiments done. Hybrid in the sense coupled experiment as well as numerical simulation. Based on these experiments, they were able to find out some values. And for hybrid, for a air conditions, for when there is no load acting on the molds, the heat transfer coefficient was found out to be 250, which was useful for our simulations, which I'm going to explain in the next slides. And then we have, then what we did is, in order to address this thermal boundary conditions, we planned two set of experiments. One was thermal cycling experiment, and the second was a glass molding experiment where we fabricated a lens. We tried to address the glass nitrogen interaction, how to model it by the thermal cycling experiments, and we wanted to address the glass mold interaction by conducting a lens pressing operation. So here you see a plano-convex lens, which we have pressed it against the molds, and then we planned this set of experiments to address the issue of glass mold interaction. So these are the temperature cycles and the load displacement curves. So I'm not going to discuss into details. So these are these information we have from the experiments. And then the glass we selected is PSK57 commercial glass, which is manufactured by Short. And these are special glasses used in lens molding. And then these experiments were performed at Hanover IPT because all the experimental facilities, the expensive experimental facilities were they were having all this set of tools and all the required things. And now once we had the fabricated samples, then we plan to measure the residual birefringence, or in other words, residual stresses in the lens. So this, we use a circular polariscope arrangement to quantify the residual stress. So here we have a polymer specimen, which is so before I show you what happens with the glass, generally conventionally these experiments are being done on polymer specimens which exhibit photoelastic effects. So these are the epoxy specimens. When you apply external load on it, you would be able to see photoelastic fringes something like this. And the stress strain and the stress optic law, which relates the optical information to the stress information, is given by this relation. And delta is nothing but the birefringence, what I showed you in the earlier slides. And C is the photoelastic constant. So if you know these two quantities, if you know C, then you will be able to quantify the stress quantity if you know birefringence. So for polymer specimens, you have very high value. So you see a lot of fringes, but when you see a glass disc, when subjected to a compression, you won't be able to see any fringes, because typically for the lens application, the photoelastic constant of glasses are in the range of 0 to 4 TPa. So this is again a separate domain of material science research, where they are trying to get special type of glasses which has got very low photoelastic constant. So that's a domain in the material science research. And so this we need to measure for converting stress information to optical information to stress information. Either of the way, we need this photoelastic constant. And for measuring the birefringence, we had the experimental setup. So where the lens was placed in the refractive index liquid, in a of matching refractive index liquid, so that the light rays can travel in a straight line. There is no refraction happening. And then there is a phase shifting technique where you capture 6 photoelastic images, and you have the intensity information from experimentally measured, and you have the analytical expressions which comes from the theory of photoelasticity. I'm not getting into the details of it. And once you do mathematical calculations on it, you would be able to compute the birefringence as well as the principal stress angle theta, what you study in solid mechanics. This is for bachelor students who don't understand. So these are the two quantities what we can measure directly. And then we performed experiments on the thermal glass disc. Similarly, we took 6 phase shifted images, and you can see that since the glass disc has got very higher residual stresses, you can see clearly a gradient of fringes. And for performing all these experiments, we had a customized experimental setup at IIT Madras. So this is the polariscope what we have. We have the light source, incoming light source over here, and we have the camera to capture the images. And the lens was placed in the refractive index matching liquid, and then all the photoelastic experiments were done. And these are the set of the results for the glass disc. So what you can see here is that you have a very nice axisymmetric distribution of residual birefringence. And from this, there was a input to the finite element simulation that we could make it as a 2-dimensional axisymmetric simulations. And you can see that the birefringence values are quite high, because the nitrogen gas is directly interacting with the glass disc during the cooling stages, and there is high amount of residual stresses. So that is what you see here at 30 liters per minute. As the flow rate is increased, the residual birefringence increases. And similarly, we did the experiments for the lens, and you can see that for 30 liters per minute, you have very low birefringence, and for 50 liters per minute, you have very high, a little bit of high birefringence over here. So this is for a plano-convex lens. And now what is the next set of task for us? So we have residual birefringence information from the experiments. We have finite element simulation where you can compute residual stresses, but you cannot compare both of them. You need birefringence also from the finite element simulation so that you can compare with the experiments directly. So how do you do that? So generally the simulation is being done is axisymmetric, what I mentioned in the past slide. So so this shows a revolved 3D model of it after we do a 2-dimensional axisymmetric analysis. So this is what we get from the finite element simulation. So in order to convert into birefringence data, so this is the equation what we have. So it is photoelastic constant multiplied with the secondary principal stress difference integrated over the thickness through which the light rays pass. So here, this is the axisymmetric model, and virtually I have to pass the light rays through this domain and through this thickness, and I have to compute the birefringence. So but we already know that light rays travel in a straight line. So that means all the information, the stress information has to lie in a straight line in order to do this integration operation. So what I did is I introduced a artificial image that is a pixelated image, and I tried to find out which of these pixels lie within the domain of the lens. So by taking a scalar quadruple product, I can find out whether which of the points lies in which particular element, and based on this interpolation function, I can interpolate the stress data which is being computed at the integration points. So based on this, I would be able to map the whole domain of the lens in this artificial image, and also I have the stress information, and I integrate this over the thickness. And in order to compute the secondary principal stress difference, this is the three-dimensional state of stress for an axisymmetric analysis. And we, from the literature of photoelasticity, one can know that the secondary principal stresses participate in the photoelastic effect. So I have taken the secondary principal stresses to compute the this term over here, and then once you compute, then you can directly integrate, and then you can get the integrated birefringence data. This is a line data what you obtain, and once you sweep it across the theta direction, you would be able to plot it in r theta coordinate to get the whole birefringence plot. And this plot can be compared with the experimental set what we have. Now, if you look at here, this integration term is fine. We can do this process, adapt this procedure over here, but you need the photoelastic constant C for different types of glasses. You need to have a photoelastic calibration step. So this was also done experimentally, and here I'm not going to discuss too much of details. In order to calibrate this photoelastic constant of the glasses, we did a 4-point bending experiment for the glasses which had relatively high photoelastic constant, which is easily measurable, and for very low photoelastic constants where the C value is close to 0, that means you will not be able to observe any significant amount of the birefringence. This was a customized, not customized exactly, but a special type of setup where the force is being acting at a particular point, and near to this point you can expect that the stress is going to be very, very high. So then it would induce some photoelastic effect. So this was also done for a special type of glasses, and for LB2000 glass, which had got relatively high photoelastic constant, we were able to measure it more accurately. And similarly, for very low photoelastic constant glass, which is having a value of 0.042, we were able to measure it precisely by using 6-step phase shifting technique. So once we have this photoelastic calibration constant from the experiments, you can substitute back in this equation over here, and then you will be able to compute the birefringence data. So this data is the simulated birefringence data and not the experimental ones, but this can be compared directly with the experiments. And now, if you look into the finite element simulation, so we have all the boundary condition information. The only missing information is the how the nitrogen glass is interacting and how to take into account those effects. So here, instead of defining any heat transfer coefficient, I have defined like a equivalent heat transfer coefficient, which takes into account this heat transfer mechanism. So this heat transfer coefficient values, we do not have any initial value, but what I did is that I used a lumped heat transfer analysis, which the bachelor students might have studied in their heat and mass transfer subjects. So using this lumped system analysis, I have the temperature as a function of time and the initial temperature information from the experiments. And by doing a curve fitting, I'll be able to compute this exponential constant over here, A, and this A is related to all the geometrical and physical properties of the glass, so which is already known. So from there, I can estimate what is the initial value of the heat transfer coefficient it should be. And based on this, I have given it as input to the finite element simulation. I simulated the birefringence data and I compared with the photoelastic experiments, and very clearly you can see that it doesn't match very well. So what I did is that using a reverse approach, we have the experimental data. I tweaked the value of the H equivalent until it matched with the experiments. So what we found out that for the flow rate of 50 liters per minute, the value was about 15 watt per meter square Kelvin. And similarly, for the different flow rates, the values were estimated as shown over here in this table. And more details, one could refer to this paper over here, which is published in Journal of American Ceramic Society. And this was the understanding what we had with respect to thermal cycling experiments. Now we wanted to address what is the issue with the plano-convex lens. How do we handle this glass mold interaction boundary condition? So this is being taken into account. The glass mold heat transfer, contact heat transfer is being taken into account by contact conductance. And if you look into the process cycle over here, initially the mold is displacement controlled, and then it was subsequently there is a force control system. So there is a control system playing role when the pressing operation is being done, and this has to be taken into account in the finite element simulation. So that was done by taking defining a user defined subroutine UAMP in Abacus, and this control system was taken into account, and the force system and force based system or the displacement control system was taken into account by using this subroutine. And here I would just quickly wrap up that we used pressure independent contact conductance, and this results didn't match very well. And when we took a difference between the photoelastic and the simulated birefringence data, the birefringence information was the difference was quite very high. The error difference was quite very high. But when we use pressure dependent contact conductance, so when as the pressing operation is being done based on the contact pressure, we change the contact conductance value. So we found out that for a critical value of 3 MPa, if you use a lower value and beyond 3 MPa, we use a very higher value, then we are able to match the birefringence information as well as the fold, the force displacement curve information, all whatever we get from experiments, all of these data we're able to match very precisely. So this was done, this curve fitting was done for a flow rate of 50 liters per minute, and then we made this value as a trial experiment for 30 liters per minute. It still worked very well. So based on this, we published some of this outcoming understandings in another paper in the same Journal of American Ceramic Society. One could refer this paper into for all the details. So now so these experimental values were then again verified with the this curve fitted values basically were verified with the experiments. And the major conclusions what we came to understand is that the heat transfer during cooling stage mechanism, we could find it out that it is basically by heat conduction, and then there is a flow field flow field which excavates this heat out, and this was modeled by using a equivalent heat transfer coefficient, and for different flow rates we obtained the values what shown over here. And there was a for glass pressing operation, pressure dependent contact conductance has to be specifically used for modeling this simulation. And these were the major outcomes what we have found from our research. Now this is totally fine. I mean, this is all what we done. We had gone deep into the issues of the glass molding operation, but the curiosity is what's next actually. So is that the all, or is there something beyond this now? Now for the next 2 minutes, I'm not going to speak anything. I would like to play a video. So please watch it carefully. And I would request the bachelor students especially to think over what kind of problems can be derived out of this process. And I would also like to mention that whatever the video I'm going to show, this technology is being developed in the last 5 years, and there is no current simulation technology which would be able to simulate this process. So please watch the video for the next 2 to 3 minutes. I'm just trying to play that. So I hope you might have watched the video quite deeply. So I have shown you two scales of products which has been fabricated by additive manufacturing. One is a very large scale product which is in meter scale, and the one is the miniature scale, maybe in order of centimeters or so. So now there has been new processing technologies for fabricating glass based products. Also, there has been attempts being made to fabricate lens also. So this is the future coming direction. And the major challenge what I want to address to the whole community, especially to the students, is that there has been no robust simulation technology which takes into account all the aspects or the difficulties of additive manufacturing process in the simulation or simulating the whole process, because the geometrical domain is growing as you fabricate the product. And the secondly, if it depends upon what scale of the product you are manufacturing, the architecture of the or the microstructure of the whole product, microstructure of the each layer, I would say, is also being evolved as printing happens. So this also has to be taken into account. So if I make a map of different stages of the process, you can look into this pictures over here. So on the processing stage, there is the material is being heated and then layers is being printed. There is a complex heat transfer modes happening here while you printing process happens. That has to be taken into account. That is number one. Second is that the material is transiting from fluid phase to solid phase. And how do we model this complete transition? So there is a domain where the fluid mechanics and solid mechanics has to interact one another. They cannot remain separate in their own respective domains. They have to interact. And this is one of the simplest challenges what I'm trying to mention here. If you look into still more details, there are n number of challenges to address the processing stage of this additive manufacturing. Now once you do that's fine. I mean, you do a processing and then you fabricate a product. That is fine, that is out. And what happens to the product? Generally, what you do in daily life, you take this product, you subject it into different kind of loading conditions. It depends what is the kind of application it is. So you could have a dynamic loading, you could have a static loading, depends totally. And if you look into this complex table kind of thing which is being printed, 3D printed, and if you take a CT scan of this image, this is how the complex architecture looks like. And the finite element simulation community, everyone knows that modeling this is just impossible in finite element simulation. You cannot take, meshing and so on. It becomes totally computationally becomes very challenging. So what you could do is you can make it as a continuum model. So you essentially maybe take it as a cylinder and you model it. But how do you take this architecture information in this continuum model? That's the major question. So how do you take this printed architecture, the porosity effects, if there is a thermal loading or there is a different kind of loading environment, how do you take into those effects? So this is a very recent challenges, how to address these kind of issues. So these are the different difficulties what you have at different stages of the product life cycle. Okay. If you still look into the bigger picture of this, let's not stick to the glass. Let's think very generically for any product. You can conceptualize this. You have product oriented research which people have to pay attention to this. Let's say there is a product which has to be commercialized now, and there has been, let's say, several issues in it. So there is one domain where people can focus on process simulation. There is a second domain where people can focus on experimental technology, where let's say CT scan technology or maybe characterization, material characterization, maybe any kind of tests, fracture tests or bending tests, any kind of experimentals domain can focus on this issue. And there is a structural simulation, guys, which could focus on structural simulation aspects, where you mathematically you take into frame the constitutive behavior of the material. And there is one domain where designing technology people can focus on over here. So these are the 4 different domains which revolves around the product oriented research. And if several academic universities or research institutes or industries can participate in of their own expertise and they interact with each other, with the common platform being the product, they can nicely interact each other, and then the outcome could be very nice. because all the challenges can be addressed very well by their own expertise, from their knowledge of their own expertise, and this could help the general community or the scientific community or industrial society. So I'm not getting into more details of this. For the bachelor students, when they are trying to look into different positions, maybe in future, if they want to get into academics, if they are interested to look into some kind of research activities, they should make a mind map into what project they go into and how would it help into in the future. So that's the bigger picture. They have to look into that and they have to understand this. And if you still this is totally fine. This is what I'm talking about research. But what is the total overall outcome, or what is the still bigger picture out of this? If you look, so everyone might be, this is a very recent buzzing word. Everyone might be aware of it. Industry 4.0 and digital twin. Industry 4.0 is something separate, where there are several agendas of industrial 4.0, and digital twin is one agenda which comes under industry 4.0. So for a few seconds, I'm playing a video. Just watch this and hear to the important information which is conveyed in the speech. So please hear to this very carefully.
Digital twins, the innovation backbone of the future, delivering virtual representations of real-world products, systems, and cities. For example, the digital twin of an electric motor not only showcases form, but also analyzes functions, from the rotation of the shaft to thermal conductivity to data from sensors and beyond. What's more, the digital twin continuously evolves, thanks to the flow of data, user experience feedback, and new input, and it's greatly impacting development, production, and operation. In development, a product's behavior can be simulated and tested long before a physical prototype has been built.
So the key important message I hope everyone might have heard over here. So there is nothing like engineering can be, there are 4 domains of engineering, I know that, but they never interact each other. So the electrical engineering, the computer science engineering, the mechanical engineering, or the civil engineering, all these 4 groups has to come into a single platform, which is Industry 4.0 and Digital Twin. They cannot be separated out. All of them interact each other, and then the whole Industry 4.0 can evolve when all of them can interact. So I'm showing you here an example project where I'm currently working on. So this is, I'm showing you a process technology for manufacturing composites. So here shows a physical process chain, and this shows a virtual process chain. So these are the different stages through which the product goes. So you have preform of the before, I mean, you mold it, you have the preforms fabrication, you mold it, you have the molded product, you have machining technology, you have quality inspection technology, you have testing technology, you have CT scan technology, and you have microscopic experimental technology to characterize what is happening at a very local scale. And on the virtual process chain, you have conceptualization of the product, you optimize the flow simulations, and you optimize the product, and you optimize the shape of the product, and then you have flow simulations, and then you have molding and curing simulations. And then once the fabricated product is out, how do we take the residual stresses present in the structure? And if you look into the microstructure of at a single point, if you look at the microstructure, this is how the fibers are arranged in a very complex manner. So this is not at all possible to model it in this structure over here. This microscopic effects has to be taken into account in a mathematical sense. So you could imagine, how do we take this geometrical information mathematically? So that's the quite challenging part. And then you have damage also over here. So this is the virtual, different stages of the virtual process chain. And there is a example paper published by us. So you can look into this if you are interested more details into it. And you could also visit this page for details of this project over here. So here, what I wanted to give you a message is that there are different issues when you fabricate a product, and different groups can interact each other, and then the processing technology can evolve. So with this note, I would like to thank you for your kind attention. I hope I have given the right set of messages to the whole academic community. And if you want to contact me, this is my email address. If you have any questions, you are always free to email me. With this, I will hand over the mic to Mr. Rajeev Ranjan and Mr. Manish Kumar.
Okay, good afternoon, everyone. I am Rajeev Ranjan, Assistant Professor, Department of Mechanical Engineering. welcomes you all in the question answer session of this webinar. First of all, I would like to thank Dr. Tarkes for this wonderful and interesting webinar. He has covered all the topics regarding glass molding. He has given all the in-depth knowledge, all the applications, all the areas where all the applications, all the areas where glass molding can be applied. Now we would like to have a question answer session, and we will take the questions asked by the audience. So first of all, the first question is basically a very simple one. If we want to go for the research field, what are the problems we face?
So this is quite funny. I mean, you basically this I mean, if you want to get into research, the first or basic thing what you need is your self-interest and your motivation. Apart from this, nothing else matters. I mean, don't I mean, I understand there are some other issues. You have to interact with your guide. I mean, there are guide problems and there are other set of things, but these all doesn't play a role when you are focused and when you are self-motivated and when you know that what you want to do in the future. After 10 years, you have to look at, you always, I ask the bachelor students, please look into the bigger picture. Do not look into the smaller picture. You always tend, it's a human tendency. It's not the problem of the bachelor students, but it's a human tendency. You always try to think the smaller picture. You are trapped in a very small problem and you start thinking around, oh, how should I solve this? Oh, how should I solve this? But this is not the bigger picture. If you solve the problem, what is happening to the whole bigger picture? So how does it help you? So that's what you have to be thinking of, and you should motivate yourself. And apart from this, other things would look very, very simple when you in your research journey, I would say.
Okay, thanks for the answer, sir. The next question is, why we use nitrogen gas? Can we use some other gases instead of nitrogen while glass molding?
Yeah, excellent question. This is a nice, I mean, someone has thought about it. I didn't answer this. You're basically heating it to a higher temperature. Okay, let's say there are metals. So what would happen if you heat the metals to a higher temperature? It would get oxidized. Yeah. So in order to, and as I mentioned, the molds has to be surface finished molds. I mean, mirror surface finished, and it will get damaged at higher temperatures. So that is why you have to place the hole into a nitrogen chamber so that the metals have get their longs last.
Okay, thank you, sir. The next question is basically, what is thermoviscoelasticity, and what is the role of this thermoviscoelasticity in case of glass molding?
Okay. These are all kind of okay. So when, as I mentioned, so you have elastic energy stored in the material. There is also a dissipation mechanism which is happening in the material. So when you have elastic energy stored, this is in the springs, and the dash spots are the which causes the dissipation. So these are the viscous part. Okay, so these are the viscous strains, I would say. And when you have a temperature effects, you have thermal strains. So thermal strains, viscous strains, and then you have elastic strains. So this is how the word is being coined: thermo-viscoelastic effects of the glass.
Okay, sir. Thanks for the answer. The next question is from Miss Aditi, and she asked that, okay, please tell something about chromatic glass.
Chromatic glass, or the colored glass, I guess. If I am whatever I am aware of, chromatic glasses are something different from what I'm talking about today. Chromatic glasses, maybe they are used in structural applications, I guess. So there are tempered glasses, so which is another class of glass products which I have not discussed or covered about here. So I guess that falls under that category. So I'm not too much aware of the chromatic glasses, but I guess it is like kind of a colored glass.
Thanks, sir. The next question is basically related to the molding process. The question is, in near future, how this precision glass molding is useful for us?
Okay, that's a good question. If you look at conventional manufacturing technology of glass, you just Google it up in YouTube or something. It takes in days to manufacture a lens. Days, and this process happens in 10 minutes, and you can straight away use into the application. There is no secondary operations in between. If you want really fast, you can design the manufacturing process. So within 10 minutes, you can take away the product and you can use it in the desired application. So that's the use. would say.
Okay, sir. The next question is regarding the research opportunity in Germany. A student Naveen Kumar has a question that if we want to go Germany for research, what we should do?
I guess he's a bachelor student. If the whole community is listening to, from my experience, what I would say is after bachelor's or after master's, it is quite easy to get into Germany. But after doctorate, it is quite very, very difficult to get into Germany because you have a PhD degree. So it should be easy enough to get into research in Germany, especially. And for bachelor's, I would say you should have a very good scores. That's quite important. Professors look at that, and based on that, they decide. And especially to the specialization, what you are especially applying. If it is mechanics, then they would look into the core mechanics course, what kind of grades you have there.
Okay, thanks for the answer. So the next question is basically regarding the industrial opportunity. What are the job opportunity in glass processing industries?
So I do not know what is the scenario in India exactly, but during my PhD days, I was also trying through in India. But outside India, definitely there are opportunities. I mean, especially if you look into Corning glass or Short Glass, these are the very famous glass companies. And the next level of glass technology is quite unimaginable. You wouldn't have really not imagined how the glass technology is going to evolve. So I would ask the student to look into in YouTube, Corning Glass, their future plans and ideas in YouTube. You could get a very nice video how they're trying to imagine things. And with respect to that, if he's a mechanical engineering, he should always think about the process simulation or mechanical simulation aspects of different aspects, maybe fracture mechanics, maybe process related mechanics, or maybe solid mechanics related concepts. So all this could be useful in the glass processing technology. So if you have that kind of a background, then getting into those companies could be easier, because they look for people. Actually, they look for this background people.
Okay, sir. Thank you for all the questions and answers. And now I'd like to request Professor S.B. Dandin, Dean Applied Sciences, Engineering and Technology, Sarala Birla University, to propose a vote of thanks and conclude the ceremony and the webinar.
Before, I would like to interrupt here. I'm sorry, I just forgot to thank Rajeev, Ranjan, and Mr. Manish Kumar for organizing this webinar. I would like to thank from my heart. So thankful for giving me an opportunity and organizing this.
Okay, thank you so much, sir. Thank you for your precious words.
Dr. Tarkes Dora P. We really thankful for your nice and beautiful talk on glass molding, that is precision glass molding for our participants. I hope, see, you very nicely elaborated the optical applications, okay, of this precision glass molding, and you have taken our students and the participants to basics of optics and physics. Students learn mechanics to solve some questions, right, or say some given problems, and you showed them the real application to the course that they go through, and precisely how exactly you animated that in your presentation. Yes, this is what mechanics is. Really, we are thankful to that you made that presentation so beautiful in the form of animation, so that it gives them more interest, right? So although we feel the mechanics is boring subject, or say it is very difficult subject, you made it very easy, and I hope our students have got the point why we learn mechanics. Thank you very much for that, and I hope the participants the takeaway, whenever they next time they see any lens they definitely remember Tarkes sir. Sir told me this is lens, okay, or by default, if they come to wear the lens, they should not wear. But if suppose say they are supposed to wear the lens, definitely they remember Tarkes sir. Thank you very much, Tarkes, for giving this opportunity to our students. And I want to make a note here, like say one of the takeaways. You nicely mentioned the domain of material science as research and simulation techniques as research. It was wonderful. And this really triggered our young minds so that they can think of doing some research activities. I thank your institution for providing this wonderful opportunity to share their work with us, your work with us. And from the core of heart, I also thank our management, our CEO sir, Pradeep Kumar Vermaji, Registrar sir, Dr. Professor Vijay Kumar Singh sir, for providing us this opportunity for our mechanical department to conduct this webinar. Really, we are thankful to the participants. Without them, this webinar would have not come to a good success. And the questions that taken for the answering and the way you handled those answers, Tarkesh, hats off to you. It was very nice. And once again, thank you very much. Thank you, Manish ji. Thank you, Rajeev ji, for providing this opportunity for our students to think in the field of research. Okay, although they are at bachelor's level, and one of the questions were very nicely attempted, like what are the scope of say research in Germany, how to reach, and you nicely covered, because I know, because I visited France many times, so I know European countries help the researchers. They call the researchers, they have nice labs, but they need the researchers. So nicely considered that case, like if they complete the bachelor, surely they can go for the masters and they can work there. So thank you very much once again, Tarkesh, for giving this opportunity, and thank you all. Now, I hope we will close this webinar, and thank you once again. Thanks a lot.
Thank you all.
Okay.
Bye.
Thank you, sir. Thank you.
Bye. Thank you.